Howdy, folks. My name is Arul Verma, and this week in CSM 28 Honors, we're going to be going over borrowing and ownership. So let's start by talking about what ownership is. Ownership is a memory management protection system built into Rust using a system of rules that are checked at compile time. There are three main rules for ownership. The first being that each value in Rust has an owner. And by value, I mean any variable or any data. There can only exist a single owner for data at a given time. And when that owner goes out of scope, the value is freed from memory. So what do I mean by scope? Because you might be familiar with scope if you've programmed in other languages before, but in Rust it's slightly different. In most languages, scope is defined as the pair of parentheses in which the declaration of the variable exists. So what do I mean by that? I mean, these curly braces are what define the scope in most languages. In C++, in Java, when you say let s equals hello, these curly braces are the braces in which s exists. And if we look at some code on the right, we'll see what I mean. If we say let I1 equals uint 256 is equal to 1, I1 exists throughout the entirety of this main function because it exists within these parentheses or these curly braces. So it exists throughout the entirety of the main function. And when we say I2 is a uint 256 too, I1 still exists within these curly braces. But I2 only exists within these two curly braces because the outermost parentheses are where I2 exists. And I2 does not exist past this closing curly brace. So if you try to access I2 or print it outside here, you'd get an error. But I1 can be used throughout all of this main function. So I can print inside here, I can print outside here, but I2 can only be printed or accessed or edited or whatever within these curly braces. So in Rust, the definition of scope is a little bit more complicated though. This is kind of the general definition, but Rust, on top of this just standard definition, an object's scope also depends on its last usage within the code. And the reason this works is the way Rust handles code is before running it, I don't know if I mentioned this in a previous lecture, I think I did, but it goes through your entire code, and I did when I was talking about functions. It goes through your entire code and it looks at exactly where each line of code is declared, and it puts that in the compiler. Like it says, oh, this is going to go in memory, we're going to store this in memory, and it's going to stop being used at this point. So each line of code, the compiler analyzes and reads through a rule set called non-lexical lifetimes. And the compiler checks where everything is used and when it stops being used. And once the compiler sees that a piece of data is no longer used after a certain point, Rust automatically frees that memory. So normally, I1 is within scope throughout these entire parentheses, but because we don't use I1 anywhere else, the compiler is automatically freed I1. If we decided to print I1 somewhere inside these curly braces, then I1 would still be in scope at that point. But after I1 has been, after its last usage in the code, the entire I1 goes out of scope. It gets freed in memory. So Rust automatically handles that. It sees that that data is no longer being used and it completely wipes it. So why do we need memory protection? Because we talked about the system where Rust looks at the last existence of memory and it just wipes it, right? So in theory, that takes care of memory for us. We don't have to handle it. Well, not really. Because what we were talking about before is the stack memory. If you notice, we were talking about uints in this case, so unsigned integers. And those are a primitive data type. Those are data types that we talked about in the first class. They're preset sizes, so 256 bits. The compiler knows exactly how big it is, and it knows where, how much memory to allocate for it. So that data all goes on the stack. All of your primitive or your basic data types, your non-vector, non-array, they go on your stack. It's smaller in size, but it's much faster to access. So data is automatically placed on that stack, and the user doesn't have to allocate custom memory. So ints, bools, characters, floats, compiler doesn't check with the user how much memory to allocate. It just does it because it knows. But for vectors, for arrays, for tuples, because those are large, those sizes aren't the same size that an integer is. So you don't know how large they can be because a tuple can have a string, and a string in it, or it can have a string, and int, and a float. And that requires a different amount of memory. So that doesn't go on the stack like an integer would. It goes in the heap, which is your long-term memory. It's much larger in size, but it's a lot slower to access in comparison. And the user must declare the amount of memory to allocate per object. Now, of course, arrays and tuples are handled by the compiler because it just reads through each variable type. But for vectors especially, you have to declare how much memory to allocate. And you do that with the keyword new. And when you want to get rid of that memory, when you want to stop using it, you have to deallocate that memory in order to prevent memory leakage, which would cause an error. So normally in other languages, especially Java, you don't have to deal with your heap memory. You don't have to allocate and then deallocate the memory because of a concept called garbage collection. Garbage collection is basically when at runtime, a daemon thread, which is an automated run thread, it'll just go through and look through which memory is not being used any longer, and it'll automatically clean it. Kind of like what Rust does for your stack memory. Oh, sorry about that. So the reason this doesn't work is because with pointers and references, it's not possible to have automated garbage collection. And we'll see an example of that in the next slide. So this is some code in C++ using pointers. And if you aren't familiar with pointers, I'm going to just briefly explain them right now. The way a pointer essentially works is I want you to think of memory like a postal box. So say we have 1,000 postal boxes. Each one can store some amount of data. So I want to store the word string hello. So I go to this postal box 848, a random number in my postal box, 1,000 postal box system. I just chose to go to 848 today, and I put the word hello inside that postal box. So if I ever want to access that hello again, all I have to do is go back to that postal box 848 and open the door, and then I can read whatever data is inside 848. So what's going on here when I say string star s2 is I'm just going to my postal box system, and I say I have a piece of paper with the word hello written on it. I'm going to open postal box 859, which is an arbitrary postal box in my entire 1,000 postal box system, and I'm going to put the word hello inside, the paper containing the word hello inside. Now, string s3 is equal to s2. All this is doing is it's storing that exact same number of my postal box system as s2. So it's also storing that number 859. So both s3 and s2 are storing 859. And what delete s2 does is it takes that postal box number at s2 and it burns the entire contents inside. So that paper holding hello inside 859 has been burned. I can't read it. No one can read it. It's gone. And now 859 is empty. So when I try and print whatever's inside 859 using cout s3, we get an error because s3 doesn't have anything inside it anymore, right? s2 burned it. But s3 doesn't know that. It still thinks it's storing the string hello. So when it tries to print, you get an error because you're like, oh my God, I'm trying to print nothing. I don't have anything to print. So that's why you can't have automated garbage collection, because so let's say we took out the explicit delete. Garbage collection would have still tried to burn s2 because s2 is no longer used after this line of code. If you look at the rest of our code, s2 is no longer going to be used. So our daemon thread would have gone through and it would have just burned the contents of s2. But once we try and access the value inside s3, the 859 postal box, we get an error because that value in s2 just got burned. And that concept of pointers is why garbage collection can't exist. And Rust has explicit rules to protect its memory to make sure that you don't accidentally cause errors like this in your own code. So pointers are still something that you'll be using in Rust. So the postal box analogy doesn't really accurately convey the concept of pointers, but it's a very good way to visualize. So there are obviously a lot more places in memory than there are in my 1,000 postal boxes, but the concept is relatively similar, where you have a place in memory that's storing your data, and you can access that memory, that data, by using those memory locations. So the way Rust protects its data, instead of using like this pointers, it doesn't have that faith in its user like C++ does to take care of its data, their data properly. So instead, Rust implements something called borrowing, which is a form of ownership to protect the data that's kept in the heap, to make sure that you don't accidentally burn data that someone else is using. And the way it does that is the concept of an owner. Because you can only have one owner, you can't burn something that someone else is using, because once you own it, no one else can use it. So the concept of borrowing is this, that if we look at this code in the bottom left, where we say s1 is equal to string from hello, and s2 is equal to s1, we don't have like the situation where s1 and s2 are both pointing to two separate hellos, or we don't have the situation where both are pointing to the same pointer like we did in the previous example with our pointers. We don't have the case where both of them are pointing to the same address in memory. Instead, what happens is S1 stops existing. S1 stops pointing to any memory at all. So if I try and print S1 here, it's not going to be able to print. It's going to error because S1 doesn't own that data anymore. S2 does. So once S2 drops out of scope, S1 also stops existing. So that memory in S1 is just gone. S1 doesn't have any address anymore. And S2 has this address for hello. And once S2 goes out of scope, it's gone. So this brings up an interesting question though, because data can only have one owner, and once the original owner gives the data to someone else, it gets freed. How do we set variables that are non-primitive that to equal each other, like strings, right? Like how do we get a situation where S1 and S2 are both equal to the same string in different places in memory? So obviously you can have both accessing the same, like you can create two separate strings, but you can also make a copy trait, right? So think about how primitives work. Primitives like our booleans, our floats, or characters, or integers, we can set those equal to each other, right? And if we say let x equal y, both in x and y will have access to different pieces of integers. Like say we had let x equals 3 and let y equals x, right? If we add 1 to our x, y will not change. And this is because of the concept of a copy trait. Primitive types have a built-in copy trait, which allows for equivalence to be used without borrowing. And all it does is it creates a new place in memory with that exact same data. And it's implicit. You don't have to call copy like you'd have to call other functions from a class. Copy is automatically done when you use that equal signs. And it just sets the data equal to each other. So both our integers store the same value, but they store in different places in memory. So you can change one and the other one won't be changed. But now that we talk about this and we've like realized it works for all of our pre-declared data types, what about for like vectors? Because vectors are something we're going to be using a lot in this class. Well, vectors have another concept called cloning. Copying doesn't exactly work for vectors because copying would just set both vectors equal to the same piece of data in memory. It would essentially do what this first one does or the second one does, where our first vector would go out of scope and our second one would point to the index. So if we want to have two vectors that have the exact same data, we clone. And clone is a built-in function for almost all classes in Rust that are pre-declared. And what it does is it takes all of the data inside our like vector or string or whatever it is, and it copies it over into a new place in memory with that exact same data and sets that new address equal to our second variable. So we can see an illustration on the right of how this would really like look. If we have S1 be our string of hello, and we say S2 is equal to S1.clone, that data of hello is copied into an entirely new piece of memory in our heap with hello again, with a whole new address. And that address is put into our pointer. And we can see the rest of the data is the exact same as well. So S2 is a whole new string. So if we print S1, S2, we'll get hello, hello. This will work. And if we try to change S2, S1 will not change. So this behavior is called a deep copy. It's used in other languages, almost all languages. Cloning is a universal concept. And it's something that you'll be working with a lot in 128 and 225. So you don't have to have that concept of cloning. Like if we want both pieces of like two pieces of data variables that store the same address, we can use the concept called referencing, which is basically using the and symbol. And referencing is a way to borrow data without taking explicit ownership of the data. So I did mention that you can only have only one person can have ownership of the data, and I kind of lied because yes, you can only have one owner, but you can also have someone who borrows that data and says, I will give it back. Just like any object in the world. Say I wanted to borrow your eraser. I promise that I'm going to give it back. And so when you give me that eraser, I am the temporary owner, but I have to give it back to you. And when I give it back to you, I'm no longer that owner. That the behavior of a borrower or owner no longer exists. So this concept of the and symbol is useful when you're trying to pass data as a parameter to a function so you can change it or do certain pieces of data. And you can't change data if you don't have it as a reference. When you put that and symbol, you are saying that, oh, I'm allowed to change this data. I'm allowed to treat this data like I'm the owner. And this is not the same as the and symbol is used in C++. In C++, when you use the and symbol, you're passing data as a reference, and you say that you're passing the data, and that allows you to change it, like you have full freedom, right? But in Rust, we have this concept of mute that we talked about in a previous lecture. So to modify data that is passed by a reference, you have to use a mutable reference. And I'll show you some code about that to show you exactly how it's used. And this is an important concept. Data passed by a reference can be either mutable or immutable. There are two types of references. And Rust only allows users to have a single mutable reference at any time. Or you can have an infinite number of immutable references at any time. You cannot have both a mutable and an immutable reference at the same time. And you have to think about how Rust protects memory to understand why this is true. What Rust is trying to do is, because what this Ansible does is it says that address in memory that we're storing, that postal box number, and Rust is trying to ensure that that data, when multiple people are accessing it, that sanctity of that data is preserved. So if I'm storing hello on a piece of paper in my postal box 859, and you also have the keys to that postal box such that you can open it and change the data inside instead of just looking at it, then we both, like if a third party comes in such that he can only look inside the postal box and read the data, right? He's our immutable reference, and you and I are mutable references. And in this case, if you try and change the data, then I know you changed the data. But for him, in his eyes, he knew that there was hello in that postal box before, but he cannot be ensured that he still has that same hello inside his postal box after you've changed the data. So he doesn't have confidence that the data he's going to read is safe. He doesn't know that that data is going to be preserved over a long period of time, that it's going to be safe for him to read that data and read it again later and see the exact same result. So you can have an infinite number of immutable references because those immutable references can't change the data. So they all have confidence that they're reading the same type of data, and they all know that they're not going to change the data. So they all preserve the sanctity of that data. But if you have a mutable reference, the person who's holding the mutable reference is the only person capable of changing that data. So the sanctity is preserved because only one person can change it, and the mutable reference is the only one with control over that data. So sanctity is preserved because only one person can access it, and they know exactly what changes they're making. So that way, Rust ensures that the people who are viewing the data know that either they're the only ones who are capable of changing it, or no one else is capable of changing it at all. And this makes sure that you cannot access memory that doesn't exist, you can't delete memory that can't exist, you can't change memory that someone else is reading, and it ensures that your data is protected, really, which is one of the big things that Rust, with this concept of ownership, is implemented for. It's making sure that your data is protected. So pop quiz. If we have the following code on the right, what happens to the ownership of our data of S? And when S2 goes out of scope, what happens to it? So particularly, we see S is our original owner of this string hello, and S2 is our borrower. So if I uncomment each respective line, what would happen? So I'm just gonna I want you to take a few seconds, pause this video, think about it, try running the code yourself with each line uncommented. I will verbally tell you the solution, and we can also try typing it up and running it and see what happens. Okay, so now let's take a look at it. If we uncomment line 16, we borrowed the value in S here on line 14. We said S2 is equal to S. So the value in S no longer exists. It got freed from memory. So in line 16, we'd get an error if we uncommented this because S doesn't exist anymore. It's gone out of scope. It's been dropped from memory. It's disappeared. On line 19, if we try and recomment line 16 and uncomment line 19, we'd still get an error if we try and run this. And the reason is because S2 has also gone out of scope. S existed only within, S2 only existed within lines 13 to 18. And when we did line 14, when we created S2, it's within these curly braces. So once these curly braces end, S2 has gone out of scope, the memory's been freed. So when we try and access it, the compiler doesn't know what S2 is anymore. So it causes an error. So this line and this line would both cause errors if you try and uncomment them. So now here's an interesting question. S2 has gone out of scope. So what happens to that data of hello? Does it return to its original owner? If we comment both lines 16 and 19 and we uncomment line 20, do you think it would print hello? The correct answer is that this would also error. And the reason is because you have to remember what Rust does with its ownership. Once data's ownership is transferred, its value is immediately dropped from memory. Like the original owner immediately is dropped from memory. So after this line of 14 happens, S is immediately freed. So it doesn't know what S is anymore. And I kind of played a trick on you when I mentioned this on line 16, that S went out of scope, but it doesn't ever come back in scope. That's not a thing in Rust. So once line 14 happens, S has been wiped, and once line 18 happens, S2 has been wiped. So there's no data in memory anymore at all. Hello has disappeared. So at this point, there's no data in memory at all, so it doesn't have anything to print. So let's take a look at some little bit more code so you can understand how mutable references work. Because I talked about it briefly earlier, but I want to show you guys how to use it because it's relevant for homework 3. So we can see that we have a string here, S, which we've declared as immutable, and it's howdy. So we have our reference 1, which is our at mutable S. And this is our mutable reference for S. We can only have one of these, remember. And we can only have one, and we cannot have any immutable references. And we can just run this code to make sure that it works at this point. And then I can show you why it would break if we tried, like how the compiler would stop us if we tried to use immutable references at the same time, or a second mutable reference. So let's create an R2, which would be our second mutable reference, mut S. And if we try and run this, we'll get another error. We can see we get an error, unused variable. And ignoring that, we can say we cannot borrow S as mutable more than once at a time. We can see we have one mutable borrow here and one mutable borrow here. And we can see that it has an error, like a full error, rather than just a warning that was there before. Now, let's say that we don't want it to be mutable. We see that error, we're like, okay, fine, we won't make it mutable. We're just going to make it a immutable reference. This would also cause an error to preserve that sanctity of data. We can see we cannot borrow as immutable because it's also borrowed as immutable. Now, what if we had said let R1 and R2 both be immutables? We can see that the only error we get is from trying to edit our code. So if we comment out line 8, this code will run because we only created immutable references and we got howdy. So now back to our original topic, which is how to create a mutable reference. So the way you do that is by using this, You use this and symbol, and then you explicitly mention that you want a mutable reference. And the mutable reference must always be for a mutable piece of data. If we had S be immutable and we try and run this, we won't actually be able to run it because you cannot borrow an immutable piece of data as a mutable reference, because that implies you're changing the data. And we already talked about the sanctity of data and the importance of that. And that's why mutable exists in the first place. So you want to have a mutable piece of data, and then you want to use and then a mute to imply that you're creating a mutable reference, and then the data that you want to create a reference of. And then from there, you can treat R1 as if it was S. You can change it in any way you want to. So you can say R1.pushString, you can do R1.append, R1.delete, whatever you want to do. Treat R1 like it's that string S. And this is how you'd pass a parameter into another function as well. If we created a function called change, and I'm not going to run this code because the syntax might not be exactly correct, but the concept is that if I wanted to pass something as a mutable reference, I did the exact same thing. I'd say stir, and then I'd give it a string. So it looks something like this. And then I do whatever I wanted inside. So it would be like append folks to stir. So it would work the exact same way, where I pass a mutable reference by using the and then mute, and then I do whatever I want to my string. So that's the main concepts for today's lecture. Here are just some quick reminders. Homework 1 is due tonight. I sent out a Discord message about it earlier today. Homework 3 is releasing tomorrow as well. So make sure you're on top of your homeworks. They're going to start coming out every week now, and they often pile up very quickly. So you really want to be on top of your work. MP0 has already been released and office hours are starting. So if you need help with your work, please come to office hours and reach out to any of the TAs or TIs, and we'd love to help you. Partial credit is available for late work until 1 week after the deadline. So you can get partial credit if you are running behind or late for work. So if you do need to turn in late, feel free to reach out and let us know, or just turn in late on regular. If there are exceptional circumstances, please do let us know, and we will try and get you an extension. Of course, if you want to follow along, this is chapter 4 in the textbook on ownership. So on the Rust language docs. So check out that textbook if you want to see this entire lecture kind of in like a textbook format. All right, thank you for listening, and then I hope to see you guys next week.